Last week we discussed the pendulum without friction and with friction, right? Without friction case, the pendulum will oscillate forever, right? And after you add this friction, it might slow down, the oscillation might disappear. Intuitively, it might converge to the equilibrium point because the amplitude of oscillation will decay with time because of friction. Something missing here. Based on this Gabriel equation, which is you can obtain this equation from the course you learn in your undergrad, such as dynamics, right? Based on this Gabriel equation, you assume there are two states, x1, x2, which represent theta and theta dot. So you can write down or you can modify this Gabriel equation to this dynamics, which is the dynamics we have talked about in this semester for the nonlinear dynamics systems. Two states, you have two differential equations. And based on this dynamics, you can find or you can select any diagonal function you like, and we choose this one. After you substitute the dynamics into the time derivative of this diagonal function, we obtain this form, which is NSD, right? Because the x1 term is missing from v dot. But intuitively, because of friction, you can imagine that this pendulum will slow down, and as t go to infinity, it will exactly, the theta will go to 0. But based on this v dot, we cannot conclude that theta will converge to 0 because it's NSD. Or you can imagine if you want to conclude theta goes to 0 as t go to infinity, the conclusion is asymptotically stable. And the requirement for asymptotically stable is V is PD and V dot is ND. But obviously, V dot here is NSD. So the best that you can conclude is only stable. But what you observe here is asymptotically stable. What's the disconnection? To bridge the gap, we need to introduce another theory called invariant set. By observation, so you can plot the phase portrait of this dynamics, which shows that it will converge to the equilibrium point 0, 0 as t go to infinity. Although there are multiple equilibrium points, 1, 2, 3. Okay, what's missing from here? Based on only these two equations, we know that v will never increase for any x1, x2 because v dot is always negative or 0 if x2 is 0. So v dot is either negative or 0, never greater than 0. So v never increase. V will decrease for whatever x belong to R exclude 0, and x1 can be any real numbers. If x2 is 0 and x1 is any R, v is constant, right? V is constant means v dot is 0, right? When x2 is 0, v dot is 0, which implies v is constant. So v is constant for these conditions. So the best from these two equations, the best you can say is x2 is 0 and v is constant. But v is constant doesn't imply v is 0. Can you further say something about x1? For v is constant, it could be, for example, if v is 5, this is the level set. Cut the label when v is 5. For v is 1 is here. Level set is like this. Okay. So for now, we can only say v is constant for x2 equal to 0. But we realize, figure out what x1 is. So to figure out what is x1, here we introduce an invariant set. So what is an invariant set? A set M is said to be an invariant set with respect to some dynamics. Okay, x dot equal to fx. If initially x is in M, then for all time x will stay in M. Then M is called invariant set of this dynamics. Invariant set means if you are initially in the set, say if you start from here, x 0. You say this is the invariant set M. So initially, x0 is in M, right? x0 is in this set called M. if that's true, and using this or based on this dynamics, x0 it can go anywhere, right? Based on this dynamics. But if xt for any t, it always stay in M. It never leave this M set. We call M is the invariant set of this dynamics. How do you guarantee this? We don't know the solution, right? We don't know this. Or how we guarantee that exists an M that x0 never leave if it initially inside the M. So go back to the previous slides. We have v dot equal to minus c over m x2 squared. And this can be used to find the invariant set. For example, so this is v, right? The height of this 3D coordinate is v. And phase portrait lies in x1 and x2. So v dot is non-positive. V is bounded by some v bar, right? If v dot is non-positive, which means it's negative or 0, right? Which implies v will never increase or never greater than some upper bound v bar. So v bar could be the intersection of this. Because of this condition, okay? It never increases, so v cannot be greater than this level. So now we want to see what's the phase portrait based on this condition. What's the phase portrait? So the projection of this is some area, right? Right. V cannot be greater than v bar. That means that the projection is here, and this is the area of invariant set, right? Because any x which involves in this area cannot go outside this area. Otherwise, if it go outside this area, the projection will be greater than, the projection to v will be greater than v bar. When you see this, it means that you can find a corresponding invariant set, okay? So what are the example of invariant set? Equilibrium point, right? If it stays in the equilibrium point, it never leaves the equilibrium point. Because at the equilibrium point, the dynamics is 0. At equilibrium point, what's the property? So at the equilibrium point, it's stationary. It doesn't go anywhere, right? So once it stays in equilibrium point, it always in the equilibrium point, right? So equilibrium point is itself is invariant set. And limit cycles, like if this is the phase, and once it enters this orbit, it never leaves this orbit, right? So this orbit is also an invariant set. And the third one is this example. V dot is equal to 0. When v dot equal to 0, which means v is a constant. V is a constant means it's this. Okay. So this area will be the invariant set. But we don't know where the x is. We only know it's in this set. Lassalle's theory is the theory that we can use to bridge the gap in the pendulum case. Because I say that in the pendulum case, we observe that the system will be asymptotically stable. But the best we can prove using the Debord function is this, right? Which cannot be concluded that it's asymptotically stable. So this theory will bridge the gap between the two. Lassalle's theory says for omega belong to D is a compact set. Compact set means it's bounded, is a bounded set. And that is positively invariant. with respect to this dynamics. Positively invariant means it's invariant for t greater than 0. We say this is d, and omega is belong to d. Omega might be somewhere here, which call it omega. So omega is belong to d, right? Omega is inside d. And it's a compact set that is positively invariant with respect to this dynamics. Means for some given some initial condition here, okay, the trajectory will always stay inside here, never leave this area, based on the dynamics of this. Okay. Then let v be some continually differentiable function, or you can say it's a Liouville function, which theta is not greater than 0, or you can say it's negative semi-definite. It's exactly the case that we confirmed before. Theta is NSD, right? For ND, it had to be negative. Then let E be the set of a point in omega where it satisfies this condition. Theta is equal to 0. So in this case, what is theta equal to 0? What does this mean? x2 is 0. And how about x1? Real number, right? Because any x1 doesn't change theta equal to 0. Okay. For this set, we say it's E. We say E is here. And M is the largest invariant set in E. Then every solution star in omega approach M as t goes to infinity. So there's another set M in E. Every solution, wherever you start inside omega, it will converge to M. This is Lasalle's theory. Maybe it's hard to imagine. I will give you an example later, okay? As we mentioned here, omega is inside D, and omega is only satisfy this condition. Because for x dot is less or equal to 0, which implies x2 have to satisfy this. It doesn't matter if you exclude 0 or not. So omega can be x2 belong to R, x1 belong to R, right? Based on this. x2 can be any number and x1 could be any number that theta will still satisfy this condition. And M, well, M is not mentioned here, but for M, you can using this condition, the dynamics. 所以它是一条线。If you go back to this face portrait, it will be interesting, okay? Because for this is a line, which is x2 equal to 0. x2 equal to 0 is this line, right? And it says this line is an invariant set. Using this condition, the best you can say is the system will converge to this line. But if you use another condition, which is the dynamic, you can further narrow down to some point on the line. And if you find those maybe only one point in the line, which is 0, 0, then you can conclude that the system is entirely stable. And that's what we want to do next. Omega is belong to D, is in D. D could be in R. This is the largest set, any real number. Okay, because omega had to be compact. So back to this example, you know all the tools, you know the invariant set, you know given this how to find the invariant set, right? Although the conclusion from this invariant set is not enough to conclude that this system is entirely stable, but we will use invariant set theory to narrow down the conditions. We find this, which is here. The next you can do is you go back to this dynamics, which is this. We are now solving the solutions. We just use this dynamics. So based on this condition says x2 will stay at 0 forever. If x2 stay at 0 forever after some time, this implies this. And you substitute back to here, the second equation. This is 0. From the second equation, x2 dot 0. And what will you say in here? What will be x1? This had to be 0, right? So x1 will be what? Will be or n pi. And it is any integer, okay, right? Include 0. So x1 could be 0. So 0, 0 will be one of the equivalent point, or it will converge to 0, 0. Okay. So this conclusion is from the contribution of invariant set. So if you don't use invariant set, the best you can conclude is this, which is a line. To find this M set, you can use whatever x in the E set that satisfy this dynamics, okay, which is this. Then you can find the M set. So did we solve this ODE? No, right? We only use this invariant set theory, right? We never solve the ODE. We never trying to find the solution of this ODE, but we still can prove it converges to x1, x2 equal to 0, 0, right? So if you start from here and you know eventually it will reach to here. But the transient response is missing, okay? You don't know what happened from t equal to 0 and t to infinity. You don't know what happened in between because they require the knowledge of the solution. But you know eventually it will converge to the equivalent point. In your first control system course, I think in your third year of in your undergrad, right? Third year. So in the first control class in your career, what did they teach? They teach transient response, right? They teach s squared plus omega n s plus omega n squared equal to 0. Something like this, right? And they teach what is rise time. This maybe x t or something, right? And this is here's 1. And they say this is some rise time, right? Okay. In which case they are discussing what happened in between, and we call this is transient response, right? How fast from t equal to 0 to reach to your state input, right? How fast? They are discussing this transient response. This is obtained, okay? The theory using to discuss these parameters with respect to the response are based on the solution of linear ODEs. So this is a linear ODE. You can solve the solution of this. You can obtain this, right? You can obtain the solution, and you compare the coefficients here. Maybe say 4, 3. Okay, you can compare the coefficient here, right? And you say, oh, if my omega is some value, then the response will be higher, whatever. But the knowledge is based on the solution of this ODE because we can solve this ODE, right? And you compare the parameters and see the higher value of this, which means this parameter is higher, they can change the solutions. In which case you can have a faster response. Okay, they all discuss about the transient response, but in double theory, there's no way you can discuss what happened in between. Okay, we only know if you start from somewhere, you can converge to somewhere because you have no knowledge about the solution to the nonlinear ODE, okay, in general. This is another corollary which is similar to the we use here. So that s equal to 0 be an equivalent point for some dynamics x star equal to fx, and that v mapping from D to R be a continually differentiable positive definite functions on the domain D, okay, and S is the invariant set which is similar to the set E defined here. And suppose that there is no solution can stay identically in S other than the trivial solution. Trivial solution means the origin. No other solution can stay in this set other than the the trivial solution, then this trivial solution is asymptotically stable. So what we did from the previous case, or in the pendulum case, is we first find out what is this set, right? And we use the dynamics to find that only 0, 0, x1, x2, 0, 0 can stay in this E set and is asymptotically stable. This is exactly the definition from this book. The question is, how did you choose or select a Laplace function? Usually when you do research, no one did before. So usually you have some reference about how they select the Laplace functions. So usually it doesn't come from nowhere. There are some references. But for nonlinear systems, the selection of the Laplace function is not obvious. But for linear systems, as I mentioned before, you can use LMI. To find the Laplace function. Linear matrix inequality. Okay, V is x transpose P x transpose. This is the Laplace function. And for some dynamics, okay. And how did you come up with this P? Usually it's from the LMI. So the LMI will be like this. A transpose P plus PA plus 2B E plus some I. Identity matrix greater than 0. So you solve this LMI. This is A is known. P is unknown. Okay. If you find, we're trying to find P using this inequality. If you find P, then this is your Laplace function. 能懂吗? So A is known, B is known, I is known. Only P is unknown. 那为什么要 solve 不要那么复杂好了，这样就好了。If you take the time derivative, you can, right? 这个微分 v dot, and what is x dot transpose? It's ax transpose, right from here. Px plus x transpose p ax, which is x transpose a transpose p x plus x transpose pa x. And that's equal to x transpose A transpose T P plus PA X， 对不对？你就把它微分 you take time derivative and substitute this dynamics, you got this. And if this is negative definite, V dot is negative definite, right? So this LMI is trying to find a P given A that this is negative. Because if this is negative, V dot is ND. So in this case, this Laplace function can be computed using LMI. Another condition for this P is P had to be greater than 0 because V had to be PD. Okay, when you're trying to solve for this P, you can use MATLAB to solve for P given A. There are many P's that satisfy this condition. Okay, but for those, you need to constrain P to be greater than 0. And I remember last year that a student asked me a question. So he said, if I find a V, given the dynamic system, I find a V and use the Laplace theory. The conclusion from that is, okay, V is PD, but V dot is not ND. Can I say the system is not asymptotically stable or not stable? I say not really, because If this v that doesn't work, we need to find another v, right? Because this still is necessary, is only sufficient conditions. Okay, if you find v that is PD and v that is ND, it guarantees this system is asymptotically stable. But if you cannot find that v, it doesn't imply system is unstable. It could be that the v you find is not a good candidate. Okay, maybe the next time you try a different v and you guarantee that it's S. That could be the case because it's sufficient condition. Sufficient means if that's true, this must be true. But if it's not true, it doesn't imply this is not true. Okay, if it's true, must be true. Not true, you can conclude it's not stable. Okay, so this radially unbounded function is usually to be used on the function v. So let v be a function mapping from D to R, which is continually differentiable functions, and v is said to be radially unbounded if v goes to infinity as long as x norm goes to infinity. Anyone knows what is x norm? X norm or 2 norm. Usually we say it's x norm. Here is 2 norm. And it's define x. For example, if x contains 2 elements, x norm is x1 squared plus x2 squared. For general case, okay, it's S norm. Similar to Euclidean distance. So this function is said to be radially unbounded if v goes to infinity as x norm goes to infinity. In example 1, it is radially unbounded, right? Because for x norm go to infinity, v will go to infinity. How about example 2? If x norm go to infinity, will v go to infinity? Not really, because of cosine is bounded by 1. If x1, x2, if you try 0 infinity, what is x norm? X norm will go to infinity. And what is v? V go to infinity, ma? No, because when x2 goes to infinity, this guy is upper bounded by 1, right? No matter what x is. And x1 is 0, so it's not go to infinity, it goes to 1. Okay. So example 2 is not radially unbounded. It's just a definition, and that will be used later. Okay, so we just first define this and give you some examples. Okay, so example 3, is it radially unbounded? No, because again, this function can be lower and upper bounded. This function is lower bounded by what? 0. Upper bounded by 1. Is lower and upper bounded by some value. So lower bounded by what? If x1, x2 is 0, is lower bounded by 0, right? If x1 goes to infinity, it upper bounded by 1. So which is similar to this, right? If x2 go to infinity, x0 go to infinity. But this could be upper bounded by 1, and for this x2 could be 0. Okay. How about this case? Example 4. Yes or no? Is it radially unbounded or not? Can you find that x1 or x2 go to infinity, but v is not infinity? If you try x1, x2 is infinity and infinity, x norm goes to infinity, right? But what is v? For v to be x1 minus x2 squared, this is 0 squared, which is 0, right? So it's not radially unbounded. Before this slides, we all discuss autonomous systems. We all only discuss autonomous system where we assume that in the dynamics explicitly a function of time. But for non-autonomous systems, usually in your dynamics explicitly depend on time. So they require another new theories to prove stabilities. So in the next few slides, we will define some functions that will be used to prove stability for non-autonomous systems. So we defined non-autonomous systems before, right? This dynamics explicitly depend on time. So here, f is a piecewise continuous, locally diffuse in X. And this is a domain that contains the origin, and the origin is the equilibrium point of this dynamics. So, did anyone know what's this expression? So f is mapping from this domain with this domain to this Rn domain, because this is the domain for the first argument t, this is the domain for the second argument x, and mapping to Rn, the state is n dimension. Here we define uniformly stable and uniformly convergent. So what is uniform? So uniform usually it doesn't depend on time. So uniformly stable is defined as given any epsilon which is greater than 0, and there's another delta function which is a function of epsilon also greater than 0. Then if the initial condition of this is bounded by the delta epsilon, then xt will also bounded by epsilon for all time. It's very similar to the definition of stable, but here epsilon and delta epsilon doesn't depend on time, so we call it uniformly. And uniformly convergent, again, the only difference with the previous one is it goes to 0 as t goes to infinity. So, and uniformly asymptotic stable means that it's both uniformly stable and uniformly convergent. And globally uniformly asymptotically stable means it's uniformly asymptotically stable for any initial conditions. Okay? If it doesn't depend on initial conditions, we say it's global, no matter where the initial condition is. So uniformly means it doesn't depend on time. Globally means it doesn't depend on initial conditions. So globally uniformly means it doesn't depend on time and initial condition. No matter where it is, you will converge to their origins uniformly. So we have defined PSD function before, right? But those are for the autonomous systems. But for non-autonomous systems, PSD has a little bit different definitions, because before we define PSD, which is usually V is now a function of t, but now here that W is a function of time, because for non-autonomous systems. So let a function W defined as Wxt is continually differentiable with respect to all its arguments, either x or t, then Wxt is said to be PSD in D if it's 0 at 0. If it's 0, W is 0 when x is 0. And it's always greater or equal to 0. For x is not at 0. Anywhere not at 0. Okay, so what is PD? To define PD, not straightforward. So this condition is same as before, as PSD, okay, but the second condition is different. So in the second condition, you need to find another PD function, which is not dependent on time. You need to find PD a non-autonomous function that lower bound this W function. If you can find this, then we say W is PD function. In contrast, this is PD, right? And for a decreasing function, it's different. So here we need to find the upper bound, okay? V now upper bound W. But in the previous case, the PD function, V lower bound W, okay? So decreasing function, if we say W is a decreasing function, if you can find its upper bound, which is a PD function, PD autonomous function. which doesn't depend on time. So for example, this is wxt because it depends not only on x but also depends on time. Before we don't see time elements in the function, but now they are in the function. They have some time elements. So is this function decreasing? Is this function satisfy this condition? Can you find a v, the upper bound is? Yes, right? What is v? Can you find a v that satisfies this condition? Because this guy always small or equal to 1, right? If a is greater than 0. Right? When t is 0, this guy is 1. And for t is greater than 0, this guy is smaller than 1. So it implies this condition where x, you can find v, which is this. Doesn't depend on time, and it's a PD function. Second example, can you find the v to show w is a decreasing function? 没办法. Okay, because it's t squared. You cannot find the upper bound of this. That doesn't depend on time. So radially unbounded functions. So is this one a radially unbounded function, which defined as for x norm goes to infinity, w will go to infinity, and uniformly on time. Means for any t, if this is this satisfied, this will satisfy. Is this w the case? 这个 w 是符合吗？ So this term will go to infinity for sure, right? But if we multiply these terms, it's hard to say. And how about this one? So it doesn't explicitly depend on time, right? But is it radially unbounded? You can try x1 go to infinity, x2 0, which give you the x norm goes to infinity, but w goes to 1, so it's not radially unbounded. In this case, even x2 doesn't go to infinity. This term might go to infinity as long as t go to infinity, right? For this case, is it radially unbounded? These time terms doesn't change w much. So check out this first. What's the lower bound of this? What's the lower bound? 它的下限是什么？ When t equal to 0, right? Which is 12嘛，是 12. Okay. And t go to infinity, is go to 1. So it's upper and lower bounded by 2 constants. So you can eliminate this. Okay. Now we don't need to care about these terms. Just look at these terms. Okay. So it's radially unbounded. You can also consider this term in the bracket first. You can consider this term first. So a lower bounded by 1, upper bounded by infinity. So we want to show that if x norm is go to infinity, this term goes to infinity, right? So this t term is lower bounded by 1. Right? It's lower bounded by 1 for t greater than 0. Lower bounded by 1, upper bounded by infinity, which implies if x2 go to infinity, the whole term will go to infinity, right? Right. So you don't need to worry about these terms. But if this term is exponential minus t, and what's the lower bound? What's the lower bound? 0. Upper bound is 1. And this 0 could be dangerous, right? It might prevent w go to infinity as t go to infinity, right? So you need to be careful. And in this case, it's not really unbounded. Like if x1 is 0, x2 is infinity, and as t go to infinity, this term can be 0, right? And w will not go to infinity, so it's not really unbounded, 懂吗? And same as the first example, right? You have exponential minus t here that prevent w go to infinity. Okay, so it's not really unbounded. So how about we modify example 4 to we change the power from 2 to 1. Is it really unbounded? Yes. No. No. Right? What happened if t go to infinity? So let's check out this term. What's the upper bound? What's the lower bound? Just check two cases, right? For t equal to 0, what's the value of this? It goes to 1 over 12, right? And for t go to infinity, it's what's 0? 0. So it could go to 0. So you cannot say it's already unbounded. 0 prevents the whole term go to infinity. Okay. So W is a function of time. It can vibrating, it's oscillating with time, okay? But no matter what time it is, the oscillation is lower and upper bounded by these two functions, okay? So we say V1 is the lower bound. V1 is the lower bound. V2 is the upper bound. Okay. Based on the definition of decreasing, we're trying to find the upper bound of W, right? We're trying to find this V2. For the positive definite PD function, we're trying to find the lower bound. For the PD function, we find the lower bound of W if it exists. And for decreasing function, we're trying to find its upper bound. We mentioned so many definitions: decreasing, radially unbounded, and PD, PSD for non-autonomous functions. So what's the motivation for that definitions? Well, that can be used to prove the stability for non-autonomous systems. For example, here, given some non-autonomous system, okay, x star equal to f, xt, it is non-autonomous because the dynamics depend on t, okay, containing the origin x equal to 0, and v is continually differentiable functions, and it's lower and upper bounded by w1, w2, okay, same as this. w1, w2 doesn't explicitly depend on time, okay. And this v is the stable function for this dynamics. So the time derivative of v, which is this, right? Because it had two arguments, one is time. So when you take the time derivative of v, you need to do the partial first with respect to time and do the chain rule with respect of, in order to introduce the dynamics of the second element or second argument, right? So this is time derivative of this v. So if you find this v that satisfies the condition, and we will say that x0 is uniformly stable because it's less or equal to 0. So this is the stability proof, the tool you can use to prove the stability for non-autonomous systems. So it's PD because it's lower bounded by W1, V is lower bounded by W1, and it's decreasing because it's upper bounded by W2. So you need to find the first step to prove the stability is you need to find the above function that is lower bounded by its PD and its decreasing function. Okay, we have to satisfy both conditions. Then you can say it's qualified to be the above function in the first step. Then you substitute dynamics and try to see if this condition holds. Then you can say it's uniformly stable. Uniformly stable. Because this V is lower and upper bounded by some autonomous PD functions. If its time derivative is smaller or equal to 0, it guarantees a decay or non-increasing, right? So it's stable, uniformly stable, because it's lower and upper bounded by some range, given some x. Is lower, say x1. This W at x1, this W is lower and upper bounded by v1 x1, v2 x2, right? And these are not dependent on time, okay? Although W changes with time, but it remains bounded, right? So it's uniformly. Remember, we say uniformly means it doesn't depend on time, okay? So it's uniformly stable. Another question is, what does this stable function look like? Here's an example. This is one of my paper. The stable function is here. Not only depend on state, but also depend on time. E1, E2 are the tracking error, okay? And its states. Theta is also states are states. Okay, so this V is bounded by states. So R is the time derivative of x tilde dot. So R depends on time. And R is in the above function. R is function of times. That's why you see time here. Based on this above function, we find the lower and upper bound. Beta 1 phi squared and beta 2 phi squared. And phi is this argument. So this lower bound doesn't depend on time, and our upper bound also doesn't depend on time. In this case, it is uniformly stable.